Just because two things share the same structure doesn't necessarily mean that they share the same shape or function. For example, if a limb or even a hand can rotate, then the same object can have different shapes, they can do different things, and perform different functions. When a molecular structure takes on different shapes, we say that it's in different conformations, and two of the same molecules in different conformations are called conformational isomers. Let's take a simple example of butane. The four carbon atoms are all bonded by single sigma bonds, which can act like an axis of rotation. If we hold the bond between the second and third carbons steady, we can see that the first and fourth carbons are able to rotate with respect to each other. At the extremes, they're either pointing on opposite sides of the central bond or on the same side. Both of these are perfectly acceptable conformations, and so are all points in between. Using software, we can map the energy of each conformation of the butane. Here we see that the molecule is at its lowest energy when the ends are pointed in opposite directions, and at its highest energy when they're pointed towards each other. We can even map the charge onto its electron density to see how the first conformation spreads out the charge evenly, while the second causes the charge to be much closer together. It's harder to show the different conformations when you don't have 3D rendering software, but we can still do it for sp3 hybridized carbons using the Newman projection. To draw a Newman projection for an organic molecule, first imagine that we're looking directly down the barrel of the axis of rotation. In our case, the bond between the second and third carbon of butane. Since each of the bonded carbons has three other bonds, that is, besides the one that we're looking down, we can draw those as three lines spaced 120 degrees apart. At the ends of the lines, we write down what that carbon is bonded to. In the case of butane, the number 2 carbon is bonded to one methyl group, that is the number 1 carbon plus its 3 hydrogens, and 2 other hydrogens. It doesn't really matter what order we draw these 3 terminal groups, because so far we only have the 1 carbon. What matters is how we draw the groups bonded to the number 3 carbon, since we're trying to show the relative angle next to each other around the axis of rotation. The bonds extending outward from the number 3 carbon should start at the same point, again because we're looking directly between the 2 carbons. But we can't do that so directly. It would look like 6 bonds extending from one single point. So instead we draw a circle to represent the rearward carbon, or the distal carbon, and then extend the bonds from that. Where the bond lines begin depend on the conformation. So let's start with the one where the 4th carbon points in the opposite direction to the first. The bond lines are then 180 degrees opposed, like this, and so are the other bonds for the terminal hydrogens. We can compare that to the 3D model to confirm that this is a fair representation. This is also known as a staggered conformation because the bonds are staggered equally about the circle. Next, let's draw the Newman projection where the 4th carbon is on the same side of the axis. The carbons should lie on the same plane, but if we try to draw them that way, it would get confusing. So we shift the rearward bonds, or the distal bonds, just a bit off for clarity's sake. Whenever the 3 bonds of each carbon fall on top of the other 3 bonds of the other carbon, we call that the eclipsed conformation. Eclipsed conformations have more electron-electron repulsion than staggered conformations, what's also known as steric strain, between the aligned atoms. So the conformation where the methyl group is aligned with a hydrogen are at higher energy than where the 2 methyl groups are staggered next to each other in what's called a gauche conformation. Conformational isomers are especially important in large biomolecules like proteins, where different conformations can inhibit the function of a protein, like the proteins in sickle cell anemia. Or it can be destroyed altogether, like when the globular proteins in milk are denatured and join across each other to form the thickness in yogurt. And so we see that even a simple molecule like butane can take on several different shapes, and the functions it can perform, the reactions it will undergo, depend on both the molecular structure and the conformation.
When knowledgeable horse people assess a young horse's conformation, the way the horse is put together, they look at the entire package. They consider the relationship of form to function. Does the horse's build and body type make him suitable for the task ahead?